a cumulative review of filing cabinet design evolution from its earliest mechanical configurations through its most current iterations, incorporating advanced materials, automated manufacturing techniques, and electronic access control systems, reinforces a central observation: the functional geometry, load-bearing principles, and organizational mechanisms embodied within the filing cabinet have remained remarkably consistent over time. This enduring continuity is not incidental, but rather the direct consequence of a thoroughly optimized design solution that continues to satisfy the persistent operational requirements of secure, accessible, and durable physical document storage. At the core of filing cabinet construction remains the rigid sheet metal carcass. This fundamental structural assembly relies on cold rolled steel, precision cut, formed, and joined using a combination of spot welding, hemming, tab and slot engagement, and mechanical fasteners. The cabinet frame exhibits sufficient torsional rigidity, flexural stiffness, and impact resistance to withstand both static and dynamic load conditions as defined by applicable ANSI, BIFMA, and ISO performance standards. The selection of metal gauge remains a direct function of the width, depth, and load rating of the individual cabinet model, with sidewalls, drawer rails, and cross members typically utilizing thicker gauges relative to rear panels, tops, and drawer bottoms. Drawer suspension systems represent one of the most technically consistent subsystems across filing cabinet history. Ball-bearing telescopic slide assemblies have remained the industry standard for the majority of vertical and lateral cabinet products. These assemblies reliably support fully extended drawer positions under specified maximum distributed load conditions, typically within the 40 to 70 kilogram range per drawer for standard office use models, and significantly higher for specialty heavy-duty configurations. Slide materials continue to be fabricated from heat-treated, hardened carbon steel or equivalent alloys, providing high resistance to raceway deformation, wear propagation, and fatigue-induced failure. Where soft, close, and dampening features are implemented, hydraulic or polymer-based damping systems are integrated without compromising the core bearing race design. Locking mechanisms exhibit persistent duality between purely mechanical keyed cam locks and increasingly prevalent electronically actuated systems. Both architectures operate on the same physical principle: a longitudinal locking bar or series of interlocking cams mechanically engage or disengage with slots in the cabinet frame or drawer rails, thereby enabling or restricting drawer motion. Electronic locks introduce additional circuit-driven actuation components, credential validation interfaces including keypads, RFID readers, or biometric sensor sand embedded microcontrollers to execute lock state transitions in response to authenticated input. Despite the sophistication of electronic variants, mechanical key overrides remain a universally implemented feature across all electronically secured filing cabinet products to mitigate failure risks associated with power loss, component degradation, or electronic malfunction. Counterweight systems, while mechanically simple, continue to serve an essential role in vertical filing cabinet safety. Rear or base-mounted counterweights are dimensioned according to drawer depth, quantity, and maximum rated drawer load. The counterweight mass distribution is calculated to ensure a stable center of gravity under all single drawer open conditions while minimizing the total deadweight added to the cabinet. Mechanical drawer interlock systems complement counterweight systems, employing either cable-driven or rod-based linkages to restrict multiple drawers from being opened concurrently, thereby mitigating tip-over risks without the need for excessively large counterweights. Cabinet anchoring provisions maintain functional relevance, particularly in seismic-prone zones or government facilities requiring enhanced stability under abnormal load conditions. Anchor kits interface directly with pre-punched mounting points in cabinet bases, transferring overturning moments into substrate-appropriate fasteners embedded in concrete, wood, or composite floor systems. Load path analysis remains an integral part of anchoring system validation, ensuring compliance with seismic resistance standards such as ICC-ES, ACON 156, or ASCE, SCI 7. Drawer interior configurability continues to be supported through modular file bar systems, snap-fit dividers, and optional accessory trays. These systems are dimensionally standardized to accommodate common file formats. Letter, legal, afferrand are constructed primarily of roll-formed steel, extruded aluminum, or high-strength injection-molded polymers. Dimensional tolerances in file bar placement maintain folder alignment within plus or minus 1 mm to prevent folder sag, skew, or lateral migration during drawer actuation. Fire resistance features maintain a specialized subset of cabinet offerings, with internal construction employing layered gypsum panels, ceramic fiber sheets, and occasionally aerogel insulation. Fire-rated models integrate intumescent door and drawer seals that expand to form thermal and gas barriers under elevated temperatures, in compliance with UL 72 EN 1047-1 or similar international standards governing fire-resistive storage enclosures. These assemblies are subject to controlled furnace exposure cycles followed by internal temperature monitoring to verify compliance with document survivability thresholds. Surface finishing processes remain highly standardized, predominantly utilizing electrostatically applied powder coating followed by thermal curing. Coating formulations comply with environmental directives such as ROACH, RE, HE, and local VOC emission standards. Surface hardness, scratch resistance, and chemical resistance metrics are validated through standardized tests such as ASTM D3000 363 pencil hardness, ASTM D4060 Tabor abrasion, and ASTM DUN1000 308 chemical resistance spot testing. Color offerings, while expanded in modern manufacturing, remain secondary considerations relative to functional performance requirements. End-of-life processing considerations are designed into the majority of filing cabinets via simplified disassembly pathways, clear material labeling, and standardized fastener types. Metal components are directly recyclable through ferrous and non-ferrous recovery streams, while polymer elements are coded for resin-specific recycling. The use of monomaterial construction for non-structural components such as drawer handles, casters, and trim elements enhances recyclability without compromising mechanical function, while predictive maintenance, IoT connectivity, and biometric access systems represent the most visible recent innovations. These remain auxiliary to the central engineering design principles of the filing cabinet, which prioritize structural rigidity, drawer actuation, reliability, and secure document containment. The integration of networked components and sensor arrays does not meaningfully alter the core box and drawer framework that has characterized filing cabinets since the early 20th century. Across all review time periods, filing cabinet design remains a case study in the incremental optimization of a static functional geometry. Each generation of design refinement, whether focused on metal gauge reduction, finish durability enhancement, locking mechanism complexity, drawer suspension smoothness, or modular configurability, has served to improve cost efficiency, user safety, and operational lifespan without substantively altering the cabinet's essential form. This review therefore concludes that the filing cabinet, in all of its iterations from early vertical 4-drawer units through contemporary biometric access lateral configurations, constitutes an optimized mechanical solution for the storage, protection, and retrieval of physical documents. The box and drawer architecture persists not as a matter of aesthetic tradition, but as a rigorously validated engineering response to the constraints and requirements of physical document management. Despite the proliferation of digital storage solutions, cloud computing, and paperless workflows, the continued presence of filing cabinets in legal, governmental, archival, and industrial contexts is expected to persist into the foreseeable future, constrained only by the rate at which regulatory, evidentiary, and archival requirements transition from physical to digital formats. Until such transitions reach full completion, if indeed they ever do, filing cabinet will remain an enduring artifact of practical mechanical engineering in the domain of physical storage systems. This completes the full technical overview, structured in accordance with the specified parameters of a dry, monotonous, highly detailed, and intentionally boring summative analysis of filing cabinet design, evolution, mechanical subsystems, material transitions, manufacturing processes, ergonomic developments, and end-of-life considerations. The development of filing cabinet designs is characterized by a series of mechanical, structural, and material optimizations dictated by the operational requirements of paper-based storage systems. Prior to the widespread implementation of filing cabinets, document storage methodologies were predominantly limited to open shelving, stacked boxes, and fixed drawer wooden chests. These legacy storage solutions exhibited deficiencies in file accessibility, linear retrieval efficiency, spatial density optimization, and document preservation under conditions of repetitive access cycles. The initial emergence of the filing cabinet in the late 19th century was directly associated with the rising volumetric requirements of administrative operations within commercial, governmental, and legal sectors. The earliest known filing cabinet variants adopted a vertical orientation schema. This structural format consisted of a monolithic upright carcass fabricated from planar metal sheets, typically cold-rolled steel, assembled via spot welding, riveting, or mechanical fasteners. The unit was subdivided vertically into a series of telescoping drawers configured for the storage of paper files, suspended along top edge rails. These rails were affixed to interior lateral drawer walls and designed to maintain consistent linear alignment of file folders during extension and retraction operations. The sliding mechanisms within these vertical units initially employed simple friction-based wooden or metal guides. Progressive iterations introduced ball-bearing slide assemblies, which yielded reductions in actuation resistance, improved load distribution characteristics, and enhanced drawer extension smoothness. Drawer slide lengths were proportionally matched to the cabinet depth, commonly adhering to dimensional standards derived from paper size conventions, such as letter or legal formats. Tolerances in slide construction were calibrated to minimize lateral drawer deflection under static and dynamic load conditions, while ensuring sufficient clearance to prevent jamming due to particulate intrusion or thermal expansion. Material selection in early filing cabinet manufacture was heavily influenced by factors of cost, availability, and mechanical performance. Mild steel sheet metal in gauges ranging from 16 to 22 was utilized based on desired load ratings and structural rigidity requirements. Thicker gauges were employed in high security or high load applications, whereas thinner gauges were designated for lightweight or economy models. Surface treatments initially consisted of paint-based corrosion inhibitors. However, advancements in coating technologies facilitated the adoption of powder coating systems, which provided superior abrasion resistance, color stability, and oxidative protection. Locking mechanisms evolved in response to operational security requirements. The simplest configurations featured single-point cam locks mounted to the uppermost drawer front, which actuated a rotating metal arm interfacing with an affixed strike plate. Subsequent improvements included interlocking rod systems, whereby vertical rods extended from the locking mechanism to engage slots located in the top and bottom cabinet frame members. These multi-point systems provided increased resistance against pry attacks and enhanced structural rigidity under torsional and impact stress conditions. Plunger lock systems also emerged, employing spring-loaded pins that engaged when the lock was activated, providing redundant engagement points and reducing unauthorized access probability. The transition from vertical to lateral filing cabinet configurations emerged primarily during the mid-20th century as spatial optimization within office environments became a design priority. Lateral cabinets were characterized by a horizontal drawer axis within a wider but shorter carcass profile. This necessitated significant revisions to drawer suspension systems, which transitioned from top-edge folder suspension rails to side-edge hanging file supports. The broader drawer width required reinforcement of bottom panels to mitigate sagging under distributed loads. Sidewalls were also structurally augmented using formed channels, doubled steel folds, or internal ribbing to counteract lateral flexion during drawer extension. The lateral configuration permitted wall-adjacent placement without obstructing access to adjacent furniture or passageways, an advantage not afforded by deeper vertical cabinets. Additionally, the horizontal drawer format enabled users to visually scan the entirety of the file contents without the depth-based obstruction characteristic of vertical drawer formats. Drawer interlock mechanisms were further refined in lateral cabinets due to the increased tip-over risk presented by wider drawer dimensions. These systems employed mechanical linkages that physically prevented the extension of more than one drawer simultaneously, a critical safety feature to maintain unit stability. Manufacturing practices incorporated progressive metal forming techniques, including stamping, bending, and spot welding. Tolerances in cabinet frame assembly were controlled to ensure squareness and drawer alignment consistency. with acceptable deviation parameters typically constrained within sub-millimeter thresholds to prevent operational interference. Base designs incorporated adjustable leveling glides or welded footplates to accommodate floor irregularities and to distribute static loads evenly across the cabinet footprint. Handle configurations transitioned from surface-mounted protruding poles fabricated from stamped steel or aluminum alloys to recessed molded grips composed of either stamped steel with integral flanges or injection molded plastic. Assemblies in later models. The reduction in external protrusions was associated with improvements in user safety, particularly in high-traffic office environments, and contributed to a more uniform frontal cabinet plane, facilitating modular alignment with adjacent office furniture. Throughout the evolution of filing cabinet design, considerations regarding fire resistance, impact resistance, and data security led to the development of specialized variants. Fire-resistant filing cabinets incorporated gypsum-based fireproofing panels encapsulated within double-walled steel constructions. These assemblies were engineered to maintain internal temperatures below critical thresholds for paper combustion during standardized fire exposure durations, as defined by testing protocols such as UL-72. Gasketed drawer seals were employed to impede heat ingress and smoke penetration. Security-enhanced cabinets, integrated reinforced locking bars, drill-resistant lock housings, and pry-resistant drawer frames. High-security models incorporated internal steel barriers, hardened steel lock bolts, and anti-tilt mechanisms constructed from reinforced alloys to withstand forceful breach attempts. Some models adopted electronic locking systems with keypad or RFID-based access controls in later development stages, further extending the functional spectrum of filing cabinet security capabilities. As filing cabinet usage expanded throughout the mid-20th century, a series of incremental design optimizations were introduced to address performance inefficiencies and emerging occupational safety considerations. One such area of development was the enhancement of drawer slide systems. Early ball bearing slides exhibited susceptibility to particulate contamination and lubricant degradation over time, resulting in increased actuation force requirements and occasional drawer binding. Manufacturers responded by incorporating sealed ball bearing assemblies, utilizing grease-retaining gaskets, and improved metallurgy for bearing races. Hardened steel components replaced lower-grade alloys, reducing long-term wear and maintaining smoother drawer travel cycles over extended operational periods. Drawer extension ratings were also standardized to support either 3/4 or full extension travel distances, with the latter allowing complete visibility and access to file contents without manual repositioning of materials within the drawer cavity. Full extension slides required increased precision in rail alignment and enhanced load distribution properties to prevent cantilever-induced deformation, particularly in lateral drawer formats with greater width-to-depth ratios. The engineering of anti-tilt mechanisms underwent several refinements as tip-over incidents were analyzed and mitigated through mechanical interlock systems. Early designs utilized passive counterweights located in the cabinet base to offset drawer-induced moment arms during extension. However, such approaches added significant unit mass and presented logistical challenges during transport and installation. Mechanical interlocks soon became the preferred solution, employing linkage rods, cams, or sliding plates that physically engage draw tracks to restrict concurrent extension of multiple draws. Tolerances for interlock engagement and disengagement were controlled within narrow specifications to ensure consistent function across production batches. Another area of incremental evolution was the structural reinforcement of cabinet carcasses. Lateral file cabinets required increased torsional rigidity to withstand shear forces during drawer operation. Manufacturers introduced internal cross-bracing systems composed of formed steel channels positioned horizontally and vertically within the frame. These structural members were often spot-welded to adjoining panels at multiple points of contact to distribute operational stresses uniformly and prevent frame racking over time. Panel fabrication techniques advanced as sheet metal processing equipment became more precise. Computer numerical control, CNC, punching and laser cutting replaced manual or semi-automated die operations, improving dimensional accuracy and reducing edge burr formation. Flange bends, hem folds, and corner seams were executed to tighter tolerances, minimizing misalignments and improving drawer-to-frame fit. Interior surfaces were often left unfinished or received a single primer coat, while exterior surfaces were finished with electrostatically applied powder coatings cured at controlled temperatures to ensure coating, adhesion, and durability. Drawer bottom panels, traditionally fabricated from flat steel sheets, were modified to include shallow bead formations or ribbed impressions. These design elements increased panel stiffness without adding significant material thickness, reducing deflection under concentrated file loadings. Folder hang rails were manufactured from roll-formed steel channels or extruded aluminum profiles with end stops or clips integrated to prevent folder migration beyond intended track limits. Locking system architectures diversified in response to both market segmentation and regulatory influences. Central locking bars, previously integrated as simple flat steel rods, evolved into more complex square or tubular profiles with increased bending resistance. Lock actuation mechanisms incorporated helical cam profiles to provide progressive engagement with minimal key rotation. Internal linkage rods were connected via swaged fasteners or riveted joints to reduce component loosening under cyclic loading. Guide lock cylinders were standardized to accept master keying configurations, facilitating hierarchical access control within multi-user environments. In higher security models, lock housings incorporated hardened steel inserts to resist drilling attacks, while anti-spin features prevented rotational defeat of the cylinder through external torque application. Drawer latch designs were revised to include spring-loaded detents that maintained drawer closure integrity during minor impact events, such as incidental contact with office equipment or foot traffic. Base structures were further refined to include integrated levelers with threaded adjustment stems allowing precise vertical alignment across uneven floor surfaces. In models destined for seismic risk zones, floor anchor provisions were incorporated into the cabinet base, with pre-drilled holes accommodating mechanical fasteners for permanent installation. Design standards for such applications referenced applicable building codes and furniture anchorage guidelines to minimize cabinet displacement during seismic events. The dimensional standardization of filing cabinets became increasingly codified during this period. Manufacturers adopted consistent nominal dimensions for vertical cabinets, typically specified in terms of overall height, width, and depth, with drawer internal clearances designed to accommodate standardized file folder sizes. Lateral cabinets followed suit, with width-to-height ratios optimized for specific file capacities while maintaining compatibility with established office furniture modularity standards. The late 20th century witnessed further developments in aesthetic surface treatments and ergonomic considerations. While early models prioritized function over form, later generations incorporated visual design elements intended to harmonize with contemporary office decor. Corner radii were softened, color palette offerings expanded, and drawer pull designs modified to reduce sharp edges and improve tactile comfort during use. These changes were executed within the constraints of manufacturing cost efficiency and did not compromise the underlying structural performance parameters. Acoustic performance also became a consideration in cabinet design. The actuation noise generated during drawer opening and closing was reduced through the incorporation of nylon or polymer bushings, dampened slide tracks, and rubberized stop buffers. These modifications were particularly relevant in open-plan office environments where noise attenuation was a priority. Thermal expansion tolerances were re-evaluated, especially for cabinets subjected to variable ambient temperatures during transport, storage, or deployment in non-climate controlled settings. Slide clearances, panel gap dimensions, and fastener stress points were analyzed for thermal-induced deformation risks, with engineering allowances incorporated into final production specifications. Advancements in filing cabinet design throughout the late 20th century and into the early 21st century focused on further optimizations in material efficiency, manufacturing process automation, security mechanisms, and ergonomic usability within standardized office environments. A key trend during this period involved the substitution of select material components in response to weight reduction targets, cost optimization initiatives, and evolving environmental regulations related to material sourcing and recyclability. Mild steel continued to represent the primary structural material for filing cabinet, carcasses, and drawer assemblies. However, gradual integration of alternative materials, such as high-impact polymers, aluminum alloys, and composite substrates, was observed in non-load-bearing components. Drawer handles, file rail end stops, anti-rattle bumpers, and glide bushings increasingly transitioned from metal to injection-molded thermoplastics. These polymers were selected for dimensional stability, ultraviolet resistance, and wear performance under repetitive operational cycles. Metal gauge optimization was systematically applied across multiple cabinet components. Finite element analysis tools were introduced into design workflows, allowing engineering teams to model stress distribution patterns under static and dynamic load conditions. This facilitated reductions in steel thickness for specific panels while maintaining compliance with load-bearing requirements and deformation-resistant specifications. Top panels, rear panels, and drawer bottoms frequently utilized 22 to 24 gauge steel, while side panels, drawer fronts, and structural cross members retained thicker 16 to 18 gauge materials. Depending on cabinet size and intended use profile, the emergence of electronic locking systems represented a notable advancement in cabinet security architecture. Early iterations utilized solenoid-actuated lock mechanisms connected to numeric keypad input panels mounted on the cabinet face. Subsequent designs incorporated microcontroller-based systems supporting programmable user codes, time delay lockout functions, and audit trail capabilities. Lock actuation signals engaged either linear solenoids or rotary motor-driven cam mechanisms, which interfaced with locking bars or drawer latch assemblies identical in form to those used in mechanical key-operated systems. Radio frequency identification (RFID) technology was later integrated into select high-security cabinet models. RFID readers embedded within drawer faces or cabinet frames authenticated proximity cards or fobs issued to authorized personnel. These systems offered advantages in access tracking, remote credential management, and reduced physical key dependency. Redundant mechanical override locks were maintained in most designs to ensure access in the event of electronic system failure, power loss, or hardware malfunction. Drawer interlock systems remained a critical safety feature across vertical and lateral configurations. Newer designs incorporated enclosed cable-based interlocks in lieu of rigid rod linkages. These cable systems reduced component count, simplified assembly processes, and allowed for smoother actuation. Cable tension was maintained via spring-loaded spools or cam tensioners, with end fittings crimped to precise tolerances to prevent slippage during operational stress events. Counterweight systems persisted in vertical cabinet designs where interlocks alone could not sufficiently mitigate tip-over risk under specific load distributions. Counterweights were manufactured from cast iron, steel plate assemblies, or, in some cases, dense composite materials formulated to meet fire safety and environmental requirements. Counterweight mass was calibrated based on drawer depth, number of drawers, and maximum rated load per drawer. Integration involved bolting or welding counterweight assemblies to the cabinet base or rear panel substructure, ensuring static stability within specified safety margins. Drawer suspension mechanisms evolved further with the introduction of soft close and self-closing features. These enhancements utilized damper-assisted ball bearing slides, incorporating hydraulic or pneumatic damping cartridges. Upon drawer closure initiation, the damper mechanism engaged to decelerate motion, preventing impact noise and reducing mechanical shock to drawer contents. Self-closing functions were implemented via spring-loaded closure assists, which engaged during the final 10 to 20% of drawer travel distance. Ergonomic adjustments were standardized following the publication of multiple workplace safety and human factors guidelines. Drawer pull profiles were revised to accommodate wider grip surfaces, minimizing hand strain during operation. The height-to-reach ratio of drawer placement was adjusted in multi-drawer units to ensure compliance with occupational safety standards, with particular focus on maximum allowable reach height for upper drawers in lateral cabinets exceeding 40 inches in width. Cabinet mobility options expanded during this period, particularly for pedestal file cabinets and mobile storage units. Casters were engineered with dual-wheel configurations composed of high-durability polymer or rubberized tread materials mounted to steel swivel brackets. Load ratings were calibrated per caster, ensuring static and rolling load compliance. Locking caster mechanisms employed either friction-based wheel locks or lever-actuated swivel locks. To drawer box construction employed either folded seam or hemmed edge fabrication techniques to eliminate sharp edges and enhance rigidity. bottom panels were flanged on all four sides and spot welded or clinched to drawer side walls, with additional riveted reinforcement in heavy-duty models. Drawer fronts were typically double-wall constructions, consisting of an exterior aesthetic panel and an interior reinforcement plate bonded via spot welds or structural adhesives. Niche specialty cabinet types emerged in response to unique operational requirements within specific industries. Firearm storage cabinets adopted locking mechanisms rated to Federal Specification FFL 2740, incorporating Group 1R combination locks or electronic locks with tamper-responsive relocking mechanisms. Medical records cabinets featured HIPAA-compliant locking systems and integrated audit trail functionality, often including time-stamped access logs stored in non-volatile memory. Plan file cabinets, designed for flat document storage, such as architectural blueprints or engineering schematics, diverged structurally from standard vertical or lateral filing formats. These units employed wide, shallow drawers supported by full extension side-mounted roller slide assemblies with load ratings exceeding 50 kilograms per drawer. Drawer bottoms incorporated centerline stiffeners, typically formed from hat-section steel channels to mitigate deflection across drawer spans exceeding 1 meter. Specimen storage cabinets for archival, geological, or biological collections introduced additional sealing features. Drawer perimeters were fitted with compression gaskets composed of closed-cell foam or extruded thermoplastic elastomers to provide dust and moisture ingress protection. Desiccant compartments were integrated into base structures to maintain controlled humidity levels within drawer interiors. End-of-life disassembly procedures were increasingly codified into product design through the application of Design for Disassembly (DFD) principles. Mechanical fasteners such as rivets, bolts, and snap-fit tabs replaced permanent welds in non-load-bearing joints, facilitating straightforward separation of steel, aluminum, and plastic components for recycling. Component marking protocols were adopted per ISO 11469 to ensure accurate identification of polymer types, with alphanumeric resin codes molded into plastic parts for downstream sorting efficiency. Material composition analysis remained a core quality assurance process throughout the supply chain. Spectroscopic analysis techniques, including X-ray fluorescence, XRF, and optical emission spectroscopy, OES, were employed to verify elemental composition of incoming steel coils. Deviations from specified alloying content thresholds triggered quarantine of affected material batches, pending root cause investigation and corrective action. Cabinet frame flatness was monitored through laser-based metrology systems, measuring deviation from planar surfaces within micron-scale tolerances. Any deviations exceeding specified limits, typically 0.5 mm per meter of panel length, required corrective processes, including hydraulic flattening or panel replacement. Drawer slide linearity was similarly validated using precision alignment jigs calibrated to National Metrology Institute standards. Quality control protocols encompassed cyclic drawer operation testing, typically involving 50,000 to 100,000 full open and closed cycles under maximum rated load conditions. Failure modes were documented, with common issues including ball bearing fatigue, slide track deformation, and fastener loosening. Corrective design iterations frequently included material grade upgrades, increased fastener torque specifications, or geometric reinforcement of high-stress regions. Chemical resistance testing was conducted on surface coatings using standardized exposure to cleaning agents, acids, and alkalis. Powder-coated surfaces were required to withstand 30-minute exposure to solutions such as sodium hydroxide, hydrochloric acid, and isopropanol without visible degradation, discoloration, or loss of adhesion. Fire-resistant models underwent thermal exposure testing per UL 72 or equivalent international standards, with thermocouple arrays placed within drawer cavities to monitor internal temperatures throughout the test duration. Weight distribution analysis informed drawer construction and base reinforcement decisions. Load simulations modeled distributed and point loads within drawers to ensure that deflection, racking, and tip-over risks remained within acceptable thresholds. Calculations factored in drawer span width, slide extension distance, material modulus of elasticity, and applied safety factors based on anticipated usage scenarios. Seismic performance testing was conducted using shake table simulations replicating peak ground acceleration (PGA) values prescribed by regional building codes. Cabinets were anchored according to manufacturer specifications and subjected to horizontal and vertical acceleration pulses. Structural failure criteria included frame deformation exceeding 5 mm, drawer ejection, or tip-over. Test results informed the design of seismic anchor kits, frame reinforcement geometries, and drawer retention systems. Thermal cycling tests subjected cabinets to repeated transitions between temperature extremes, typically -20 degrees Celsius to +60 degrees Celsius over multiple cycles. This testing validated dimensional stability of slide mechanisms, retention of coating adhesion, and preservation of fastener integrity under thermal expansion and contraction conditions. Acoustic performance validation involved measurement of drawer actuation noise within anechoic chambers. Maximum allowable noise levels were set based on occupational comfort guidelines, with typical thresholds ranging from 30 to 45 decibels during drawer operation. Noise reduction measures included the application of viscoelastic damping materials to panel interiors and the substitution of metal-on-metal contact points with polymer isolators. The cumulative effect of these incremental optimizations was the production of filing cabinets exhibiting high structural reliability, extended service life, modular configurability, in compliance with a broad array of regulatory and performance standards across multiple global markets. Despite substantial technological advancement in auxiliary features such as electronic locking, seismic anchoring, and biometric access, the fundamental cabinet form factor comprising a rigid carcass enclosing a set of mechanically guided drawers remained functionally unchanged from its inception over 100 years prior. Industry forecasting for filing cabinet design increasingly centers on the intersection of traditional mechanical storage systems with emergent digital technologies. Although the core market for filing cabinets remains stable within specific sectors such as legal, governmental, and archival storage, demand trajectories demonstrate a gradual decline in general office environments correlated directly to the continued proliferation of digital document management systems. Predictive maintenance technologies represent one area of exploratory development in high-end filing cabinet systems. pilot implementations have incorporated embedded sensors within drawer slide assemblies to monitor parameters such as actuation, cycle counts, vibration signatures, and drawer alignment variance. Sensor arrays typically utilize accelerometers, Hall effect sensors, and strain gauges interfaced with low-power microcontroller units, MCUs. Data acquisition is transmitted wirelessly via Bluetooth Low Energy, BLE, or Zigbee protocols to centralized facility management dashboards. Analysis of sensor data enables predictive identification of failure modes, including bearing degradation, fastener loosening, or structural fatigue in drawer slides. Maintenance alerts are generated when monitored parameters deviate beyond predefined thresholds, allowing for preemptive servicing and mitigation of unplanned downtime in critical storage environments such as records, archives, or laboratory specimen repositories. Further advancements in access control are projected through the adoption of multimodal biometric systems. Conceptual models incorporate facial recognition, voice print analysis, and fingerprint scanning, either individually or in combination, to improve both convenience and security. Authentication algorithms are integrated with cabinet-mounted embedded processors, executing real-time biometric comparison using encrypted on-device data stores, thereby reducing dependency on cloud-based credential databases. Emerging prototypes also explore integration with Internet of Things IoT ecosystems within office environments. Filing cabinets equipped with IoT gateways communicate with broader building management systems, allowing for automated access logging, environmental monitoring, and dynamic space utilization analytics. For example, drawer usage frequency data can inform office layout optimizations by identifying underutilized or high-traffic storage locations. Smart drawer content recognition has been proposed utilizing embedded RFID readers positioned along drawer interiors. File folders fitted with passive RFID tags are tracked in real time as they are inserted, removed, or relocated within the cabinet. Inventory management software associates each RFID tag with specific document identifiers, enabling instant verification of file presence without manual inspection. Error-checking algorithms detect mismatches between expected and actual file inventories, prompting corrective action. Material science innovations under evaluation include the application of graphene-enhanced coatings for improved surface hardness, corrosion resistance, and electromagnetic shielding properties. While cost constraints currently preclude large-scale deployment, prototype testing demonstrates significant enhancements in scratch resistance and thermal conductivity when graphene-infused powder coatings are applied at nanometer scale dispersions. Alternative substrate exploration includes the development of lightweight honeycomb core panels encapsulated within thin steel or aluminum skins. This structure yields high stiffness-to-weight ratios while reducing overall material mass by approximately 30 to 50% relative to solid sheet metal constructions. Structural integrity assessments indicate acceptable performance under typical filing loads, provided that edge banding and core bonding processes meet adhesion strength criteria. In response to the growing emphasis on sustainability, biocomposite materials composed of recycled natural fibers combined with thermoplastic or thermoset resin matrices are under limited evaluation for use in non-structural components such as drawer, dividers, handle assembly, and decorative trim elements. Mechanical property testing confirms tensile strength, impact resistance, and dimensional stability are adequate for auxiliary functions, but remain insufficient for primary load-bearing structures without significant reinforcement. Declining demand trends in traditional office markets have prompted filing cabinet manufacturers to diversify product offerings into hybrid storage systems. These systems combine conventional drawer-based storage with integrated charging stations, network cable management, and secure storage for electronic devices such as laptops, tablets, and portable drives. Drawer interiors are fitted with foam-lined compartments and tamper-resistant USB or power outlets, secured by the same electronic or biometric access systems applied to document storage. Fire resistance standards are undergoing review to accommodate the thermal sensitivity of electronic media stored within cabinets originally designed for paper documents. Enhanced insulation systems utilize aerogel blankets combined with phase change materials, PCMs, to maintain internal temperatures below critical thresholds for both paper combustion and data loss in magnetic storage media during fire exposure event. Electromagnetic shielding features are incorporated into certain specialty cabinet models designed for secure storage of electronic media or classified documentation. Shielding is achieved through the application of continuous conductive mesh layers bonded to internal surfaces, providing attenuation of electromagnetic interference (EMI) in accordance with MIL-STD 285 or IEEE STD 299 compliance thresholds. End-of-life recycling processes are further optimized through the adoption of single material fastener strategies. Wherever feasible, manufacturers utilize steel on steel or aluminum on aluminum rivets, bolts, and snap connections, facilitating material stream purity during mechanical shredding and downstream materials separation. Plastic components are increasingly consolidated into monomaterial families, primarily polypropylene or polycarbonate, to enhance recyclability without the need for manual disassembly. Disassembly automation is an emerging research focus, with experimental robotic systems designed to deconstruct filing cabinets by identifying fastener locations using machine vision systems and executing precision removal using tool-changing robotic arms. Initial pilot systems demonstrate throughput rates that meet or exceed manual disassembly labor while improving worker safety and materials recovery efficiency. Forecasted evolutionary design trajectories suggest continued incremental optimization rather than radical structural transformation. The fundamental box and drawer configuration persists as the optimal geometry for physical document organization in applications where digital redundancy is not feasible or permitted due to regulatory constraints, legal mandates, or archival preservation standards. Additional design modifications are anticipated in the form of dynamic load balancing drawer mechanisms, incorporating motor-assisted actuation with adaptive force modulation based on drawer load profiles. Such systems reduce user effort variability and mitigate wear differentials across drawer slides, particularly in high-usage environments. Smart environmental controls are proposed for archival-grade filing cabinets. Integrated temperature and humidity sensors monitor internal conditions, triggering alerts or automated responses such as desiccant regeneration cycles or microclimate adjustments via thermoelectric cooling elements. These systems aim to preserve sensitive materials, such as photographic negatives, microfilm, or historical documents requiring strict environmental control. Cabinet structural monitoring continues to evolve with the application of embedded fiber optic strain sensors. These sensors provide continuous measurement of deformation along critical load paths, enabling real-time structural health assessments. Anomalies in strain distribution patterns are flagged as potential indicators of fatigue, fastener failure, or improper loading, prompting preemptive maintenance or corrective action. The sustained persistence of filing cabinets as a relevant storage solution, despite digital transformation pressures, is primarily attributed to legal, archival, and security considerations. Sectors such as government records management, law enforcement evidence storage, and museum archival preservation maintain consistent demand for secure, physical storage systems capable of enduring decades of service under strict environmental and security parameters. Future design revisions will continue to align with the dual imperatives of functional reliability and environmental sustainability. Material reductions, enhanced recycling pathways, electronic integration, and predictive maintenance capabilities represent the primary avenues for product development over the next design cycles.